Hi, hello. This is part 4 of chapter 5. So in this part of the lecture, we are going to learn about how to name ions and ionic compounds. Okay. So this is the first time you're going to learn these names, and I want you to pay attention when you learn these names because there is very specific way that we are going to use to name these ionic compounds. And let me remind you here that here, we are only learning about how to name ionic compounds, and the rules that you are using in this topic are only applicable to ionic compounds. Please, again, please do not take these rules and apply it to onto a covalent molecules because covalent molecules naming follows different set of rules. And in this part, again, we are just going to learn about how to name ionic compounds, and they were applicable only to ionic compound containing molecules. Again, what are ionic compounds is a combination of metal and non-metal is an ionic compound. So let's learn how to name these ionic compounds. So first, we are going to learn how to name both a cation and anion individually, and we are going to slowly build up to how to name a compound. First, learn about how to name a cation. A cation is anything that has a positive charge, right? So for example, if you have a monoatomic cation, which means a metal that lost electrons, any metal or any species that lost electrons is called cation. And in any compounds, your cation is always going to be a metal. And how you would name it is you would name it by adding a word ion to the metal or the cation. So for example, if you have potassium with a +1 charge, you would name that cation as potassium ion. That's it. And how do you name an anion? An anion is anything that has a negative charge. And in ionic compounds, anions are non-metals because they accept electrons. So how do you name these compounds is you would name these compounds by changing the suffix, the tail end of the molecule. So you would change the tail end of the molecules by removing the last 3 letters of its actual name and by adding the new set of letters IDE, IDE. So for example, let's say you have chlorine. Chlorine, last 3 letters ends with INE. Or so you would take those, you would take out those 3 letters and add word "ide." And for oxygen, again, you would change the last couple letters and your name is here ending with "ide" instead of oxygen. So when I say oxygen, which means it is a neutral oxygen, and when I say oxide, which means it is an oxygen with a -2. Because the charges on oxygen atom is always fixed, has to be a negative charge. And if I say chlorine, I'm referring a neutral chlorine element. But if I say chloride, I'm referring to a chlorine with a -1 charge. So I'm referring to a chlorine anion. So this is going to be our new normal. Just by looking at the name, we have to predict the type of charge it is going to have. Is it a cation or anion? So cations, names like this, the name of the metal, and at the end you have an ion. For anions, your name should end with "ide." In addition to those, here I'm just going to show you few metals with a different style of naming than what you just saw. So here, the style of naming that you see here for potassium ion, we use them for metals that have a fixed cationic charge. What does that mean is any metal from group 1 is always going to have +1 charge. Any metal from group 2 is always going to have +2 charge. Any metal from group 3 is always going to have +3 charge. These are fixed, reliable charges. However, if you have a transition metal properties are different, and sometimes they would exhibit different possible charges, different cationic charges. So because you have this ambiguity on the transition metals, what do we do instead of simply naming them as, a metal ion? We follow this new style of naming only for the transition metals. That is, you name the metal name and you would use the Roman number to indicate what type of charge that particular element has, and you would name it. So here we have Fe plus 2 and Fe plus 3. So to indicate iron has plus 2 charge, we used Roman number 2. And we just named the metal as iron. And to indicate Fe plus 3, you name the metal iron and you put Roman number 3. And here clearly I indicated what is the old style naming is and what is the new style naming is. In the past, like a century ago or more than a century ago, people were using these names of ferrous and ferric. Sometimes you might see them in the textbooks, but they were not popular anymore because it's not clearly giving us it's not clearly giving us the charge right away. You just need to remember, oh, ferrous means plus 2 and ferric means plus 3. Now, because of this ambiguity, people thought that it is nice to not to follow those and go with the fixed Roman number notation to avoid any ambiguity. That's why we have this new style naming of naming the metal and its charge using the Roman number. So simultaneously, for example, for manganese, manganese exhibits 3 different cationic charges. So to differentiate one from another, what do? We name that metal and we include its charge. We name that metal, we include its charge. We name that metal, we include its charge. Again, what is one thing common in all of these is they were transition metals. Transition metals, not all of them. Some of them exhibit different charges. So that's why we use these numbers to indicate those charges. So now I'm going to show you a chart that I collected from internet. Somebody did a nice job on collecting all of this information. Excuse me. Somebody did a really nice job on collecting all of this information with each atom ionic name, when it is a cation, when it is an anion, and summarized it. And I thought it's highly useful, so I included it here. And I'm just going to go over a couple regions. So these are reliable main group elements. Group 1 and group 2. You can relate them because they're going to form the fixed charges. And so are this group 3. Excuse me, something in my throat today. And these are reliable non-metals. I think I should include this one too. So you can name them in the form of ide, and these in the form of cations. These are cations, and these are anions. And here I'm referring to the transition metals. Transition metals come up with, excuse me, transition metals come up with more than one possible charge sometimes. See here, let me highlight a few of them. Iron and manganese. Chromium has 2 charges, vanadium has 2 charges, titanium has 2 charges, nickel has 2 charges, copper has 2, cobalt has 2, so does palladium and platinum and ruthenium and niobium, all of these, and so does mercury and thallium, lead, bismuth, and polonium, and antimony and tin. All of these has multiple charges. So, and some more here that you see multiple charges. So because you don't know which one is going to have multiple charge, we just put the Roman number style oxidation number next to the metal so that people know which charge metal you're talking about, which charge cation you're talking about. Only you don't have to include cationic charge whenever you're referring to any metal from group 1, excuse me, any metal from group 1, group 2, and group 3, except thallium here, which has the charge here. So all of these has the fixed charges, so you don't have to use a separate Roman number to indicate what is that metal is. But any other metal, you have to include the charge so that people aware that, oh, this is not reliable, that's why he included the charge. Okay. And we are going to refer to this chart a lot. Well, not me, but I suggest you refer to this chart a lot until you get really familiarized with the names and their charges. Okay. And one thing I really need you to get the understanding is the charges on the anion. Each one of these groups is going to have. This group 7 element is going to have a -1 charge. This group 6 element is going to have a -2. This group 5 anions are going to have -3 charges. They are going to be very crucial for you to identify the correct name, because as I said, these transition metals are not reliable in what charge they are going to have. Only reliable way for you to know what charge this metal is going to have is by referring to the charges on these anions, which are fixed. So we are going to use them later in a couple of slides when we start, trying to name the molecules. So what we have here is what I just showed you previously, what we have it in the book. In the book, some of the main or popular cations are mentioned, and here you can see some from group 3, aluminum, barium, well, group 3, and some from group 2, barium, cadmium, calcium, cesium, all of these, some of the common ones, and some you see with the different charges: chromium +3, cobalt +2, copper +1. So whenever you have a transition metal, you have a charge next to it automatically. So if you were naming again, I'm saying it multiple times because we, the students, easily overlook it. If you have a cation, there are two different styles of names cations follow. One without charge, one with charge. Only metals, only cations that arise from metals that doesn't need to have charge next to them is if the metal is coming from group 1, group 2, and group 3. Any other metal must have the charge next to it. Here you can clearly see chromium is not a metal from group 1, 2, 3. That's why you have charge. And so is cobalt, and so is copper, so is copper. So is iron here, lead here. But you don't see any charge on lithium because it's from group 1. And you don't see any charge on magnesium, but you see charge on manganese, and you see charge on mercury, but you don't see any charge on potassium, and you don't see any charge on silver, sodium, strontium, and tin. You see charge, and on zinc you don't see any charge. There were a few that doesn't need to show any charge, but even if they were non-metals, some exceptions, but most of the times they do have the charge next to them. And if it is anions, and anions are not many, and these are mostly all the anions that we have. So you just need to remember those names. Some of them are very easy to predict, like bromide, chloride, fluoride. You change from bromine to bromide, chlorine to chloride, fluorine to fluoride. And some of them are, you just need to remember how we happen to say them. So hydrogen change to hydride, iodine change it to iodide, nitrogen change it to nitride, oxygen change it to oxide, sulfur change it to sulfide, and phosphorus change it to phosphide. All right, so what you just learned so far is knowing what charges are present on the cations and anions from periodic table. As I said, cations that are reliable are group 1, 2, 3 that has respective charges of +1, +2, and +3. And anionic reliable charges are group 7 is -1, group 6 anions have -2 charge, and group 5 anions have -3 charge. Anything else, you cannot trust them. Okay, so now let's say you have an ionic compound, you're required to identify the ionic, you know the name, but you don't know in what ratio they were combined with each other. So for that, you need to come up with a ratio of these charges to be neutral to each other, because each ionic compound must have a neutral charge. Ionic compounds will have a neutral charge always, and they react with its counter cation or anion in such a ratio to come up with the neutral charges between them. So let's look into a problem here. So let's say you have a cation and anion, example, let's say aluminum oxide. So I gave it with the two elements that are participating in the ionic compound as aluminum and oxygen. So aluminum, if you look at the periodic table now, you will find it in metal category in group 3, which means it will have +3 charge. And oxygen is from group 6, an anion, non-metal, so will have a -2 charge. So they don't have the same magnitude of charges of +3 and -3, or +2 or -2, which means you cannot have them in 1:1 ratio and hoping to get a neutral ionic compound formula, right? If you just put 1:1 aluminum and 1 oxygen next to each other, what is your overall charge is going to be is +1. You cannot have it because ionic compounds are electronically neutral. So what do we do to solve this one is you come up with the lowest possible ratio that they can present with each other to get the overall neutral charge. So this is how we do it. So you try to identify in what ratio they will have, and most logically, this is how it works. The charge is going to indicate what is the subscript of the other charged species. So aluminum +3 charge is indicating it requires to have 3 oxygen elements, and oxygen -2 charge is indicating that it requires to have 2 oxygen elements. In this way, 2 times of +3 aluminum and 3 times of -2 oxygen will result in neutral charge. This is how you will come up with a neutral ionic compound formula. And this is something that I ask you to do a lot in this chapter. So you need to, get used to this style of trying to identify chemical formula that is electronically neutral. All right, so this is kind of flowchart for us to follow to identify ionic compound name. Okay, so there are 2 different styles and they separate one from another here. So let's go from start. If the compound contains a metal and a non-metal, and if your compound contains at least 1 metal and a bunch of non-metals also, you have an ionic compound. Okay. First thing you need to check if you have an ionic compound or not. Once you know that you have an ionic compound, your next goal is to identify is your life is going to be easy or hard by looking after which type of metal you have. Do you have a metal from group 1, 2, 3 or any other metal that is not from group 1, 2, 3? So if you have a metal from group 1, 2, and 3, your life is going to be relatively easier because they will have fixed charges. And there are some more that has fixed charges as well that you need to remember. But just look for element 1, 2, 3, elements from group 1, 2, 3. If you have them, this is how you would name. You just name the metal, right? You name the metal, and you name the non-metal with "ide," and just add them together. That's it. Let's see. Let me take an example. Let's say you have NaCl. Na is from group 1, so I'm going to follow this left side method. How do you name it? Is Na name from periodic table is sodium. And chlorine is a non-metal. I need to name it in the fashion of "ide." So chlorine changed to chloride. This is how I name. And NaCl, I name it as sodium chloride. Okay. So here, the other type is, a little bit more challenging, is if you don't have a metal from fixed charges range, group 1, group 2, group 3. So in those cases, you have to dig in a little bit more. You need to include the charge on the cation, the metal, with a Roman number, so that people specifically knows which type of compound you have. So for that, let me take an example. You have, let's say, FeCl2. How do you name that compound? To name this compound, we know that Fe is not from group 1, 2, and 3. So you're going to use the right side method. So you are going to name the compound iron, just like here. We have an iron. But you need to include the Roman numerical charge. What is the charge on this one? How do we know? So iron can exhibit multiple charges, iron 2 or iron 3. How do we know if it is going to have +2 charge or +3 charge? Just by looking at iron, we cannot tell. The other clue is present in chlorine. Okay, so chlorine has a fixed charge of -1. And how many chlorines we have? 2 of them. Okay, and what did we learn about the overall charge of any ionic compound? 0. So which means if you have one iron, what is the charge in the parentheses should be to make this whole charge FeCl2 0 is +2. So +2 is the charge on iron. So you put that here. So now this is important. It doesn't matter how many chlorines or how many non-metals you have. You just name it as "ide" fashion, as 1. So even though you have 2 chlorines, you still name the chlorine Cl2 as just chloride. Because it is redundant to say that you have 2 chlorines. It's just confusing. This Roman numerical number 2 is going to take care of that. Oh, there are 2 chlorines. That's why Fe has +2 charge. Okay. Let me use another example. Similar example, FeCl3. Okay. So FeCl3, again, we don't know what charge iron has, but we know what charge chlorine has. So chlorine has -1 charge. You need to have overall charge of 0 for the FeCl3. So to identify what is the charge on iron, where there is 1 iron, to get overall neutral 0, we should have +3 here. So which means in FeCl3, the charge on iron is 3. So to name this molecule, you name it as iron. In the parentheses, you say 1, 2, 3. And even if it is Cl3, you just say, oh, excuse me. Chloride. Sorry about that. The computer is having problem in letting me write chloride. Let me try another area. Iron 3 chloride. There you go. I can write here clearly. You see, you don't have to tell how many chlorines there are because Roman numerical number is going to take care of it. So please do not make that mistake. You are not required to do it. Okay. All right. We are going to revisit what we just discussed and practice some before we conclude this topic. To name ionic compound, these are the things you need to do. You need to name your cation in the fashion of just the metal name. Like, if you have a K plus, you call it as potassium ion, but to name the metal in the ionic compound, you just exclude ion. You take it away, ion. And you would use Roman numerical whenever needed. Like if the charges are, not fixed, like if it is from group 1, 2, and 3. And for the non-metal part, the anion, you would name the anion as you would normally if it is alone. Let's say if fluorine has a -1 charge, you would name the fluoride with -1 charge as fluoride ion. But whenever you're trying to name in an ionic compound in combination with a cation, you again exclude ion. You exclude that. So, for example, if you have NaBr, this is how you would name. Na has fixed charge, and Na plus is called as sodium ion. So you would exclude the ion, and the Br has -1 charge. Br with -1 charge is called a bromide ion, but whenever you're trying to name them as a pair in an ionic compound, you would remove the ions and you would say sodium bromide. And here is a familiar example that I just discussed, FeCl2, iron Cl2. So iron has no fixed charges, so you need to include the charge in Roman numericals, and you need to tell what ion you had by saying chloride. And FeCl3 again has no fixed charge on ion, so iron, Roman number 3, and chloride. See, we are not saying how many chlorines there are, but we are just including the Roman numerical charge, which is going to take care of how many chlorines there are. So if you see the name, let's say iron chloride, iron 2 chloride, and iron 3 chloride, you need to think yourself that, oh, iron is connected to 2 chlorines. That's why there is Roman numerical number 2. And when you say iron 3 chloride, oh, iron must be connected to 3 chlorines. That's why there is Roman numerical number 3. Okay, let's practice what we just learned here. So the question is asking us to name these compounds of, oh, I'm about to say these names, but I shouldn't. Okay, I'm going to give you a chance of naming these compounds. Usually students do a pretty good job in this section. So remember what we just discussed? Name the cation, but remove the ion name, and if the charge should go into there, include the charge in the parentheses, and name the anion, but remove the ion. So first one, CaO. Ca is from what group? Ca is from group 2, so it doesn't need to include the Roman numerical charge. And oxygen named as oxide. Okay, now Ca is from group 2 and oxygen is from group 6. Looks like 1:1 charge, so calcium doesn't need any Roman numericals, so name should be calcium oxide. No Roman numericals required. Now Mg3 and 2. Mg is from group 2, magnesium, and the nitrogen is from group 5. So magnesium is from group 2, so it doesn't need any Roman numerical number to include, so you don't have to worry about that. And nitrogen is named as nitride, and you just need to say magnesium nitride. Do not worry about including any charges. You just need to know how to draw this combination of magnesium and nitride by looking for the neutral combination between magnesium and nitrogen, but you do not need to tell how many nitrogens there are, how many magnesiums there are. It is left to our wisdom of knowing that ionic compound should have a neutral electronic charge. Last one, Fe2S3. There is an iron. Iron doesn't have a reliable fixed charge, so you need to include what is the charge on this iron is going to be. So we need to do a bit of a work here. So whenever you have a metal from transition metal range that doesn't have a fixed cationic charge, you need to use the help of your non-metal to predict what is the charge on your metal is. We have sulfur, and sulfur is from group 6. Sulfur is from group 6, and group 6 elements is going to have -2 charge because it's 2 electrons away from group 8. So let's look for this neutral combination. Okay, you have a 2 irons, right? 2 Fe, and we are going to figure out what should go into that box. And you have a 3 sulfurs, and each sulfur has charge of -2. You need to have overall neutral charge. So 3 times -2 is -6 here. And how do you get +6 here? And you're multiplying with the 2, which means you should have +3 here. That is how you would get +6, and -6 is equal to 0. What does that mean is your irons here has a +3 charge. That is how you would identify the charge. So your name is going to be iron 3 sulfide. Okay. I am really big on you naming the molecules, right? And also I'm really big on you able to identify the chemical formula given a ionic compound name. You need to be able to do it in both ways. For that, you would have to use this equation sometimes. Okay. All right. Let's work the other way. Deduce the formulas of the following compounds: mercury 2 chloride. Okay. All right. Let's work on that. And lead 2 bromide and potassium nitride. So this is what our plan is going to be. We are going to identify if you have a metal with a charge or not, and let's see if they're going to form overall neutral electronic charge by identifying the ratios of metal and non-metal required to form in a compound. Mercury, they already gave the clue here. They say mercury has +2 charge, right? And chloride, we said -1 charge. I got this mercury +2 charge from here. Now, +2 and -1. Do you have overall neutral charge? No, currently. So how do you get the overall neutral charge is, you cannot change this one. It already has fixed charge. You can always change how many non-metals you're going to have in this case. So if you have 2 chlorines, it's going to solve your problem. So your chemical formula is going to be HgCl2, right? HgCl2. Now let's look into next problem. Lead Br2. So lead is given its charge as +2, and we said Br. Br is from again group 7, so it should have -1 charge. You're hoping for overall neutral charge. Currently you don't have it, so you need to increase number of bromines you have. So if you do that, your chemical formula is going to be PbBr2. That's B. Let's see, C. Potassium nitride. Okay. There is no charge next to metal, which means it must be from group 1, 2, 3. Potassium is from group 1, and group 1 elements is going to have +1 charge. Okay, and nitrogen is from group 5, and a group 5 non-metals is going to have a -3 charge. But you are hoping for overall neutral charge. So now, in this case, the low number is metal. So you need to increase that +1 to +3. How do you do that? Is by taking 3 potassiums. Again, if you were a little bit confused with this advanced method, you could always use this formula. potassium with a +1 charge, nitrogen with a -3 charge. You are hoping for overall 0 charge. How do you get +3 for -3 is by having 3 here. That's why I put 3 here. So which means potassium nitrate formula is going to be K3N, 3 potassiums and 1 nitrogen. Okay, going to erase the ink and show you what I got here. So we could compare PBBr2 and K3N. That's all from this part. I'll see you again in next part.